exponential growth and decay. Just to warn you, there's probably going to be a bell in about 4 minutes into this video. But exponential growth and decay is something that grows or falls faster than linear does. And our models for those are y is equal to a 1 plus r raised to the t power, and y is equal to a times 1 minus r to the t power, where a is the initial amount, r is the rate, and the rate needs to be set as a decimal. For example, 32% needs to be 0.32. And time, or t, is time, of course, and that's whatever units they say. Some problems might be per second, per year, what have you. Now, 1 plus r is called the growth factor. And 1 minus r is called the decay factor. In other words, if this part of the equation, the 1 plus r, the 1 minus r, if it's bigger than 1, that's a growth factor. If it's less than 1, that's a decay factor. Yeah, so let's do our first example here, show you how and why this stuff works. There's a pond stock with 2,000 fish. How many fish, oh, they increased at 5%. How many fish are there going to be after the first year? Well, the first year, the initial amount is 2,000 times 1. No, the fish are growing. We're increasing in fish, so it's going to be 1 plus 5% would be 0.05. Raised to the first year would be the first power. So pull out your handy dandy calculator. Let me get mine out. So now it might be a little bit less than the 4-minute mark for that bell. But I'm going to put this in our calculator. 2,000 times, you could put 1 plus 0.05, or you could put 1.05, because that's what 1 plus 0.05 is, right? Raised to the first power. You should get 2,100 fish. Right, what would that be after 2 years? Do the same thing, so it's going to be y is equal to 2001.05 raised to the 2 power, so just do second enter, change that 1 to a 2. You should get about 2205 fish. So the first time went up about 100. Second year, it went up by 105. It's increasing not at a linear or constant pace, but at a different pace. 3 years is going to be y is equal to 2,000. 1.05 raised to the third power. So second enter, change that to a 3. You can see that's 23. There it is. 2315. Now, because we're talking about fish, I don't want to be chopping up fish. That's gross. So we're going to round it down to the nearest fish, 2,315 fish. So after 3 years, there's that many fish. How does this formula work? Let's explore that a little bit. So, y is equal to, so our initial amount is 2,000. That's our initial amount part. And then it's going to grow by 1 plus 0.05. That's 1 plus our rates raised to the first power, let's say. So after our first year, if we were to distribute the 2,000, we'd get our original 2,000 fish back, but then we'd get a 5% growth on that 2,000 fish, which would be 0.05. Oops, excuse me. Oh my goodness. 0.05 times 2,000 fish, and that's our extra 100 fish. You add those together, and that's where our 2,100 comes from. But then year 2 is about to happen, and we're going to add another 5%. Right? Since this is 1.05 squared, that means there's 1 plus 0.05 times another 1.05. Now, if we were to distribute our fish from the first year, 2,100 times 1, and then 2,100 times a 5% increase, that's where we would get our 2205 fish. All right, and then the third year would be another 1 plus 0.05. Distribute the 2205 fish to the 1, and then a 5% growth, and that's where we come up with our 2,315 fish. So this exponent allows us to do this calculation 3 times just in a tidy little package like this, and our calculator will churn it out for us. All right, now that is an example of an exponential growth. Let's talk about an exponential decay. Your car is a bad investment, y'all. If you buy a car, it's probably going to go down in value. So the first thing we're going to do is write an exponential decay model for the value of the car that we bought here. Our model is going to be y equals, our initial amount is 24,000 times 1 minus, it's minus because it's decreasing in value by 16% raised to the t power. That's our model. Notice there's 2 variables here, y and t. Your model is always going to have 2 variables. Then the second part of this is asking for what is the value after 2 years. So after 2 years, that's where we plug in 2 for t. So this would be 24,000 times, you could put in 1 minus 0.86 or 0.84, that's the decay factor, to the t, and you put that into your calculator, and long story short, you should come up with, I believe, $16,934.40 in 2 short years. That's a bummer, right? So it says graph the model on your calculator and sketch below. Let's graph this bad boy. So we're going to do 24,000 raised to, times 0.84, then raised to, except you need an 8 in there, Smith, raised to the t power, or in this case, it's going to be x. Now, most of us are probably in our standard negative 1010, negative 1010 window, and when you graph it, well, shoot, nothing happens. Now, let's think about why nothing happens. What is our, at time 0, t is our x value. At time 0, what is the value of our car? Well, our initial amount is 24,000, so our y is the value of the car, is way up there at 24,000. So we have to change our window. How about we make our y maximum? Let's make our y maximum 25,000 to make sure we see it. And I'm going to change my y scale to go by 1,000. Probably doesn't matter much, but let's see. Then graph it. Oh, snap. There it is. There's our graph. So let's make a little sketch of this. Ain't got to be fancy. This up here is 24,000. And it looks like this thing kind of curved down. Oh, goodness. I don't know why that bump happened, but it looks something like that. This thing also said describe the window that we use. Well, our x value, our x was still, I'm going to put bracket, negative 1010. And our y value was from, if you recall from our window, negative 10 up to 25,000. Describe the windows that somebody could go and recreate your graph and see what you were looking at. So there it is there. Now, part C, it says use the graph to estimate when the car will be half the value of 12,000. All right, so in other words, what's happening here, 12,000, when is the value of car? That's y. 12,000 is equal to our initial amount times 0.84 to the t power. Now, one way that we could solve this as we get deeper in this lesson, in this unit, we'll learn how to solve this algebraically, but for right now, we're going to solve this graphically by, this is already our y1 equation inside our calculator. We're going to put in 12,000 in for y2. So go into y equals, and in y2, put in 12,000. You press graph, and I think some of you might know where we are headed here, right? This thing goes and intersects it right there, we're going to find the intersection point. The way we do that, second trace, number 5, and then all you got to do is press enter, enter, enter. The intersection, your calculator is pretty good at it. You should come up with the points 3.98, comma 12,000, right? So how long will it take for our car to be about half its value? It'd be about 4 years. It would take about 4 years. So our calculator is a powerful tool in solving these things. Let's go down to the next example. It says, consider the function y is equal to 65.4 times 1.43 raised to the t power. Hopefully, your notes now say, is this growth or decay? Well, here's the thing. Since it's number after our initial amount, right? This is the initial amount. Is this a growth factor or a decay factor? This is growth because it's greater than 1. So this is growth. What is the growth rate? Hopefully your notes say, what is the growth rate? Well, the rate is 43% because it's 1 plus the percent. So this is a growth of 43%. That brings us to page 2. Now, another type of exponential growth has to do with banks and interest. Now, interest in bank accounts, right now this seems like a math problem, but I'm going to tell you what, y'all, in about 5-10 years, this is going to be fascinating to you. When it has to do with your money, interest is fascinating. Anyways, so there's this hairy, scary formula here. A is the amount in the account. P is the principal. Now, the principal is the original amount. N is the number of times your money is compounded. Now, we'll talk about what that means here in just a minute, but it's how many times a year it's compounded. T, of course, is time. But for these problems, time is always measured in years. That's important. And then, of course, the rate. R is the rate, and that's still as a decimal. So you got $2,000. You're going to put an account that pays 6%. If you find an account that pays 6%, you need to grab that thing right now in 2016. Tell you what. Find the balance after 3 years if compounded annually. So this is going to be y equals our initial amount, or excuse me, not y. A, right? A is the initial amount is 2,000 times 1 plus, now our rate, R divided by N. Our rate is 0.06 divided by N. If annually means it's going to be compounded once a year. You put your money in on January 1st. Next January, they're going to compound it once for you. They'll give you 6%. Raised to the N, in this case 1, times T. Now that we're putting this in there for 3 years, so T is 3. All right, so pull out your calculator. Go back to our home screen here. And we're going to put in 2,000 parentheses 1 plus 0.06 raised to the, or excuse me, 0.06 divided by. Now here's the thing. I'm going to throw a curveball at you now. Instead of just putting in 1, I want you to put, and why would you put in 1, right? Well, here's the thing. We're going to do this a few times. I want you to put in 1.0 for N. Close parentheses, raised to the, now if you have the classic, make sure you put parentheses. If you have the math type, same, just you're up inside the exponent. Again, put in 1.0 times 3. And then close parentheses. Hopefully, no matter which operating system you have, you should have got $2,382.03. Look at that. In 3 years, you made a couple Benjamins there. Right? Now, what happens if we compound it quarterly? Well, that's going to be A is equal to our initial amount, 2,000, times 1 plus 0.06. But this time, we're going to compound it 4 times a year, quarterly, 4 times a year. Raised to the N is still 4 times 3. Right? Now, Let's see what happens first. Inside your calculator, press second enter, and anywhere where we put that 1.0, change that to 4.0. So 1.0 is now 4.0. That first one, leave that guy alone, right? But the 0.06 divided by 4. There we go. Press enter, and hopefully y'all got $2,391.24. Huh, how about that? Same amount of money, same amount of time, same interest, but we got a little bit more money. Here's what's happening here. We put our money on January 1st here, and at the end of the year, on January 1st again, they said, hey, you want 6% on your money? And we said, yes, please, and they gave it to us, right? But when we're compounding it quarterly, we put it in on January 1st. Then 3 months later, so that'd be the beginning of April, April 1st, the bank says, hey, would you like a piece of your 6% in interest? And we said, yes, please. So they gave us a quarter of the 6% interest. All right. So then our 2,000 became a little bit more. So then in June, 3 months later, they said, would you like a little bit more of your 6% interest on the money that we already gave you a little bit of interest on before? And we said, heck yeah. And so they did another piece of the 6% on our 2,000 plus money before. So every time they add interest, they're doing just a piece of our interest rate, but they're doing it more often. And so we're getting more interest throughout the year. If you got questions about that, holler at me in class. I'll break it down. But that's why we get a couple more bucks, right? So here's the thing. Press pause really quick. Hook up monthly and daily. What do you think is going to happen the more time you compound it? It's going to get a little bit more money. So go ahead and press pause. Let's see if we agree. Hey, so did you pick up on why I had you put in that 1.0? So when we do it 12 times, second enter, put this 12 point and make this, too much. 12 point times 3. Did you get $2,393.36? Made $2 more. And then hopefully for this one, did you get $2,394.40? That's what you should have got for those two. So notice the more we compound it, the more it increases just a little bit. Now, what if we want to find out how much we're supposed to start with? We want $5,000. How much we got to start with if we're going to put in an account that pays 3% compounded quarterly? Well, we want 5,000. So that's the amount in the account. But they're asking how much do we start with? That's our initial value. That's P. That's our principal. Then it's going to be 1 plus our interest rate is 0.03 divided by quarterly 4. Raised to the 4 times 3 years, right? So we're trying to solve for P. Now, many of you might have gone and reached for your calculator and you're going to solve it by graphing. Instead of that, this is a number, right? So pull out your calculator, but just go to the home screen here, and we're going to put in parentheses 1 plus 0.03 divided by 4 raised to the, I'm just going to put in 12 because 4 times 3 is 12. That, right? So you get 5,000 equals 1.09p, right? So then we're going to take 5,000 divided by, now we just divide by our answer. Second answer. And P is about $4,571.19. So in order to get $5,000 at 3% interest, you need to start with almost $5,000. 4,500. Takes money to make money, y'all. That's it for exponential growth and decay. Smith out!